Hi, everyone, and welcome back to Physics 4A. Today, we will be talking about oscillations. So let's go ahead and get started with simple harmonic motion. Now, this is going to be a type of periodic motion, and that is any motion that repeats itself at regular time intervals. So something like playing the guitar with strings, that is something that's called periodic motion. Okay, because as we pluck the strings, the string will go back and forth and then eventually die out. Okay, and there's a couple terms that we're going to need to understand before moving on to understanding simple harmonic motion, and that is going to be period, or T, which is the time to complete one oscillation in the absence of friction, and the units are in seconds. We have mentioned this before, but I just want to go over it again. And then we have frequency, which is a lowercase f, and that is the number of events per unit time. Okay, and the units of this is hertz, Hz. And 1 hertz is actually 1 cycle per second, or 1/seconds, or 1 second's inverse. Okay. And to relate these two, the frequency is equal to 1 over the period. Okay. Now, one cycle, or a cycle, is one complete oscillation. So we'll be seeing this word oscillation, oscillatory motion, a few times throughout this lecture. So just understand that that is a cycle. Okay, a cycle is one complete oscillation. Okay. So let's go ahead and do a quick example. There's not going to be many examples throughout this portion of the chapter, this whole chapter, but it's pretty straightforward. So this example states, consider a medical imaging device that produces ultrasound by oscillating with a period of 0.4 microseconds. Okay. Then it asks, what is the frequency of this oscillation? Okay, so we have the period T is equal to 0.400 microseconds. Remember that micro, so in this case, microseconds, this is equal to 10 to the negative 6 seconds. Okay, that's what micro means. That mu here, okay, this symbol. So we are wanting to find the frequency. So the frequency, like it stated in the last slide, is 1 over the period. Okay, so we'll take 1 over our period, which is 0.400, and I'm going to go ahead and convert it to seconds. So times 10 to the negative 6 seconds. And let me get my calculator and put it in there. So 1 over 0.4 times 10 to the negative 6th. And I get frequency of 2.5 times 10 to the 6th. And this is in inverse seconds, or 2.5 times 10 to the 6th hertz. Okay, hertz is pretty typical, but if you prefer to write 1 over seconds, whichever works. Okay. All right, so moving on now to the characteristics of simple harmonic motion. And this is called SHM for short. Okay. We want to go ahead and characterize this. In simple harmonic motion, the acceleration of the system, and so the net force, is proportional to the displacement and acts in the opposite direction of the displacement. Okay, so let's look at this diagram over here. So we've got the simple harmonic oscillator, which is going to be this block here. Okay, and the system that oscillates with simple harmonic motion is called a simple harmonic oscillator, or SHO. Okay, so you'll be seeing these throughout the lecture. And so this is a simple harmonic oscillator, and we've got a spring attached to this block, okay? And you can see that it has been stretched out, okay? Remember that where x equals 0 is the equilibrium point, okay? So just pointing that out. So this block has been stretched away so that the spring stretches. And so now we have some force here, some net force. Okay, notice that the normal force and the force due to gravity, or the weight of the object, are the same, so they cancel. Okay. So again, the acceleration of the system here is acting in the opposite direction of the displacement. So this object has been displaced here. So this is like D, right? The displacement. And so our force is in the opposite direction here. Excuse me. Okay. Now, if we did the opposite, if we went ahead and from the equilibrium point, pushed the block this way so that the spring is now scrunched up, okay? So it's not elongated, right? It's now compressed. We say that now our force is going to be in the opposite direction, okay? So now it's pointing, say, in the positive x direction. If we go ahead and say that this is x and y, oops. So that's the positive direction, okay? So this is now the force that is being applied here, okay? All right, what if we have, let's see, this one here. This is going to be very similar to these other ones. Actually, it is the same. Okay. What I want to point out here is that the maximum displacement from equilibrium is called the amplitude. Okay, so the maximum we can displace this block here, so from x equals 0 to x equals a, that is going to be the amplitude, okay, the maximum displacement of that block. Okay, then we have that the period of a SHO, or simple harmonic oscillator, depends on the force constant, and we have talked about the force constant in the past, K, and the mass of the system, and we will see that here in a moment. Okay, so let's go ahead and talk about some equations of the simple harmonic motion. Okay. So these are a few different graphs. They're all kind of showing very similar things. Okay, so this first figure here, we have that our equilibrium point is at x equals 0, so that would be this line here. Now we start with the mass way over on this side at maximum, right? This is the maximum position, okay, in the amplitude, okay, and so then we release it and we watch what happens. Okay, so we release it, there is a net force going in the opposite direction of the displacement, which makes sense. Okay, then it continues on through that equilibrium point. Okay, then as we get to this compression state, okay, or we get closer to the negative of the amplitude, or the minimum, I can say the minimum, okay, the minimum point, the force changes to the other direction, okay, because now we have a compression going on, and it will continue that way. Remember that our force is going to be in the opposite of the displacement, okay? And then it continues, and then it switches back and goes back to the equilibrium point, then back to maximum, back to the equilibrium point, and then back to minimum, okay? And so we notice that this is a sinusoidal wave, okay? So with that information, we are able to plot position versus time. And as time goes on, we're starting at our amplitude, or our maximum amplitude. Okay, let it go. And for one full oscillation, so from peak to peak, or one full oscillation from where it begins and then goes down to the minimum, back to the maximum, is one period. Okay. Okay, so this is defined as one period, one oscillation, okay, one cycle, all the same idea, okay? Now, they have also compared this with the mass on a spring, the position versus time, and we see the same type of sinusoidal waves, okay? So now what we've done is create an equation to describe that simple harmonic motion, okay? And it is as follows: x of t, so the position with respect to the time, is equal to the amplitude a times the cosine of 2 pi over capital T, or the period, times lowercase t, which is the time at which you're taking your measurements, okay? Or it is the amplitude times cosine of omega t. Now, recall that omega in the past we defined as the change in the angle over the change in time, or d theta dt. And in this case, the period is constant. So the angular frequency is then just omega equals 2 pi over t. Okay. All right. So let's go ahead and move on with this. Sometimes we have a phase shift, and that's exactly, or very similar to what we have in the past. So we have in the past one, in the equation that we just saw, we had this, right? X of t equals a cosine omega t. Now, what happens is we just have to change that angle by a little bit, or whatever amount. And so that is our phase shift here, okay? So this is a typical cosine theta plot, okay? We have that cosine goes from 1 all the way down to -1, back up to +1 in 2 pi angle, okay? Now, in this case, we will have we'll have a phase shift. So it just changes that a little bit. Okay, so just notice the slope change, okay, on either side here. Okay. Okay, whoops. So I wanted to talk about the equations of motion for the simple harmonic motion. Now, I was going to derive these for you. So we start with x of t, okay, and that equals a cosine omega t plus our phase shift. Now, from this, we can take our derivative, right? So if we want to find the velocity, our velocity is just equal to dx dt, right? Okay, so then we'll take that and we get, let's see, so we'll have a, the derivative of cosine is sine, negative sine of omega t plus phase shift, and then take the derivative of the inside here, which is going to be omega. Okay, so now we have our v of t. Okay, and this is the same as this. So notice that this says negative v max sine of omega t plus phi, okay, they have defined V max as A omega, okay, or amplitude times omega, okay? But it's the same exact thing that I just found. So then we want to find our acceleration. Our acceleration is going to be dv dt, right? So we do the same thing again. We have negative A omega. Now take derivative of sine here is going to be cosine of omega t plus phi. And then again, take the derivative here, and that's going to be omega again. Okay, since it's with respect to t. So now we see, again, we have the same equation here, and they have defined A max, or the maximum acceleration, as A omega squared. Okay. All right, so let's go ahead and do an example. Let's see. A 2 kilogram block is placed on a frictionless surface. So there's our mass. A spring with a force constant K equals to 32 Newton per meter is attached to the block, and the opposite end of the spring is attached to the wall. The spring can be compressed or extended. The equilibrium position is marked as x equals 0 meters. Work is done on the block, pulling it out to x equals 0.02 meters. The block is released from rest and oscillates between x equals 0.02 meters and x equals negative 0.02 meters. The period of the motion is 1.57 seconds. Determine the equations of motion. Okay, so when it says equations of motion, you want to find x of t, v of t, and a of t, okay? You want to describe its entire motion. Okay, so we have the mass is 2 kilograms. We have our force constant, K, is equal to 32 Newton per meter. We have our equilibrium position is x equals 0 meters. And we have the distance that we pull it out. So that's going to be our A. Okay. We have our period, which is T equals 1.57 seconds. Okay. So let's look at what we need. We need our A. We need our omega. Okay. We don't need our T. Our T is going to be our variable here. Okay. We don't have a phase shift. It didn't indicate one. So that goes away. So we have x of t is equal to A cosine omega t. So we need to find our omega. Okay. So let's go back. And remember what omega is equal to. Omega is 2 pi over the period. Okay. So I'm going to go ahead and write it over here. Omega equals 2 pi over the period. Okay. So if we plug our period in there, let me grab my calculator and do it. 2 pi over 1.57. We get a period of 4, I'm sorry, the angular velocity omega 4.00, and this will be in radians per second, or yeah, I'll just put that just for that there. So we have then A, which is going to be our amplitude. Okay, so that's going to be 0.02 meters times cosine of omega, which is 4.00 radians per second times t. Okay. So that's x of t. Now we want to find v of t. And v of t is going to be negative a omega sine omega t. So negative a omega sine of omega t. Okay. So I'm going to go ahead and put a times omega into my calculator. So my amplitude is 0.02 times my omega, which is 4. And I get 0.08. And this is going to be should be in meters per second. So we've got radians per second times meters. Yep, meters per second times sine of 4.0 radians per second times t. And then last of all, we have our acceleration, which is going to be negative a omega squared cosine of omega t. So again, I'm going to do this in my calculator real quick. So I have my amplitude times my omega, which is 4 squared. So I have negative 0.32 meters per second cosine of 4.0 radians per second times t. Okay, so now these are my equations of motion of this block. Okay. All right, so go ahead and move on. Looking at period and frequency of a mass on a spring, I should say on a spring. Okay, so consider a block on a spring on a frictionless surface. So we know that the force due to a spring is equal to negative kx. And we'll go ahead and set that equal to our net force, right? So this will be F net force, okay? And what am I trying to solve here? Plugging in the motion. So let me go ahead and rewrite this as m times acceleration. Remember, acceleration is equal to the second derivative of x with respect to t. So I'm going to go ahead and put that there. So d squared x over dt squared equals negative kx. Okay. Now, we can plug in these values. So we're going to plug in our x of t is equal to oops, come on, eraser, a times cosine of omega t. Okay, we're going to go ahead and plug those in to the x's. Okay, or we can remember also that a of t is equal to, a of t is equal to negative a omega squared cosine omega t. Oops, a, capital A, omega squared cosine omega t. And I did forget the phase shift there. So this should be plus phi in there. Okay. This is a general case. Okay. So now we can go ahead and plug that in. So we have m times, this is our acceleration here. So I'm going to say negative a omega squared cosine of omega t plus phi. Okay. equals negative k times a cosine omega t plus phi. Okay, now we can cross out the likes. So we've got this cosine term here and here. We also have a on both sides and a minus on both sides. So we have m omega squared is equal to k. Okay, now from this, we can find a few different relations like we have down here. Okay, so we can solve for omega. So omega would be equal to k over m, and then square root both sides, right? So omega squared is equal to k over m, square root both sides and get that one. Okay, there. Okay. From this, we can also relate it to our period. So remember that period t is equal to, actually, omega was equal to t, no, 2 pi, sorry, I'm trying to think in my head, over t, remember, 2 pi over t, okay? So that's how we get to there. Then we remember that f is equal to 1 over t, okay? Or our frequency is 1 over the period, okay? So this is our relations that we gathered from looking at a block on a spring, okay? So now we can use all of these equations in order to determine these different terms if we need to, okay? Now we can look at vertical motion and a horizontal spring, okay? So let's first look at this situation here. So this spring will be at rest at some height, y0, or y naught, okay? Now, when we place a object on the end of that spring, the spring gets elongated, okay, by some amount, and this is called delta y, okay? And delta y is equal to y naught minus y1, okay? Where this right here is y1, okay? So we've got that related here, how these relate. And we can also find the force of that spring, or on that spring, and that'll be equal to k delta y, where delta y is y naught minus y1. Okay. Now, looking at this figure here, this has a lot of information, but we're again just looking at oscillation of an object on a spring. Okay, so say we have some particle or ball at the end here, and we have it compressed, okay, at the start, and then we release it and it goes down and then stops at some point and then goes back up to that compressed point and then goes all the way down to the most elongated point and so forth, okay? And we can plot the different motions. So we can plot the position, the velocity, and acceleration all versus time, okay? So in this first one, we have a amplitude is the maximum that this particle attached to the spring will move, okay? So it'll go from A to negative A, okay, over our period here, T, okay? Then when we look at the velocity, remember that our velocity is now some kind of sinusoid, right? So this was a cosine, now it goes to sine, okay? And actually a negative sign. And notice how it looks very similar to our cosine, just shifted over, right? So say this hump is from there. So it really just, it's like the wave shifted over by pi over 2. Okay. All right. So with the velocity, we go from 0, because that's our starting point, right? V equals 0 at our starting position. And then when we release it, it'll be at some maximum here, right? This will be at some V max, but our V max is going to be negative, right? This is all negative values. And then here we will be at 0 again. Oh, wait, we start at 0. This will be V max, I'm sorry. This one here will be V max, okay? And then at this point, we go back to 0. Okay, so this is 1, 2, 3. 1, 2, 3, okay? And then again, we gain velocity. So now we are at positive V max, okay? And it continues in this way, okay? And then we go again back down to 0. Okay, so this is how the velocity works in regards to this oscillation. Okay. All right, now let's go ahead and look at acceleration. Remember, this is going to be something like a negative cosine, right? So again, it's going to be very similar to this first one with position, since it's a positive cosine, but now it's negative. Whoops. So wherever you will have a maximum position, will have a minimum or negative maximum acceleration. Okay, so that's how these are related here. So we've got, at this starting point, we have a negative A max, or negative maximum acceleration, okay, at the starting point. Then as we move on to here, this will have no acceleration. And then at the bottom, we'll have the highest acceleration, A max, okay, and so forth. So notice this first one here and the other ones is that the period does not change. Okay, the period is constant throughout this motion. Okay, so from one maximum to the next maximum, it is the same throughout. Okay, the period. Okay, and then this is just another figure showing the unstringed length and the equilibrium position, and then all the way down to the minimum here. Okay. All right, and remember that the equilibrium position is basically where it's at rest. I try to think of it as the most comfortable position, wherever that system doesn't have to do a lot of work. Okay. All right. So I'm going to go ahead and pause here, and then we will continue in our next video.